Today may very well be the single most important lecture in the entire course, because today we're going to introduce a concept called the mole. If you have difficulty understanding this particular lesson, watch it again and again and again until you feel that you do have a good understanding of this concept. It's kind of that important. You really do need to understand this well in order to move on successfully with little future frustration. Before we get into the definition of the mole, I think it would behoove us to ask a very fundamental question. Why did chemists invent this particular concept? To answer that question is relatively simple. Chemists invented the mole concept because it was very important to them that they have a way to count atoms and molecules. For example, let's suppose you wanted to run a chemical reaction between barium atoms and iodine molecules to form barium iodide. For the moment, we'll just call these atoms and molecules, even though barium iodide is an ionic solid, and it might be difficult to run the reaction in the actual way it's written down here. That's not important for what we're discussing. The equation for this reaction tells us that one atom of barium reacts with one molecule of iodine to produce one formula unit of barium iodide. Now, in order to run this reaction and not have anything wasted, we need a way to count barium atoms and iodine molecules. In fact, we need to count them out in equal numbers for this particular example. But how in the world can you count atoms and molecules? You're probably already aware that atoms and molecules are unimaginably small. We can't see them in the normal sense. So how could we possibly count them out? Sounds like an impossible task. And they wanted to be able to do this many, many years ago. Or let's even imagine that we had tremendous eyesight and a really, really small pair of tweezers, and somehow we could stand there going 1, 2, 3, counting out barium atoms and going 1, 2, 3, counting out iodine molecules. You're probably aware that atoms and molecules are so small that it would take the entire population of the world about 18 bonzo-zillion years to count out the atoms and even a tiny speck of something. So what are we supposed to do? How can we count things we can't see in numbers that are unimaginably large? That's what the mole concept allows us to do, and that's why it's so important. Okay, so how does this thing work? Well, remember in the last lecture when we talked about the relative weights of atoms and molecules? For example, the atomic weight of barium is listed as about 137.3. The units are AMUs, but that's not important to us at the moment. The atomic weight of iodine is 126.9. But since an iodine molecule contains 2 atoms of iodine, the molecular weight of iodine is twice that, or 253.8 AMUs. What do these numbers tell us? Well, as discussed in lecture number 8, these numbers tell us that an iodine molecule is heavier than a barium atom. In fact, if we want to compare these two numbers quantitatively, we can actually determine how many times heavier an iodine molecule is compared to a barium atom. The ratio of the weights of one iodine molecule to one barium atom is 253.8 to 137.3, or 1.85 to 1. This ratio tells us that an iodine molecule is about 1.85 times heavier than a barium atom, just under twice as heavy. Let's draw an analogy. Imagine in your mind a football player, a big football player, a lineman or something, and a cheerleader. The football player weighs 253.8 pounds, and the cheerleader weighs 137.3 pounds. Clearly, the football player is heavier than the cheerleader, and the ratio of their weights is 1.85 to 1. Again, the football player is a bit less than twice as heavy as the cheerleader. Now let's do a mental experiment. What if the football player had an identical twin and the cheerleader had an identical twin? Now I take two football players and compare their total weight to the total weight of two cheerleaders. How would the relative weights of two football players to two cheerleaders compare to the relative weight of one football player to one cheerleader? Think about that for a moment. Well, hopefully you realize that the ratio is still 1.85. In fact, as long as we take equal numbers of football players and cheerleaders, this ratio will still always be 1.85. If we had 10 of each, the total weight of the football players to the cheerleaders would be 2,538 pounds to 1,373 pounds, which is still a ratio of 1.85. And, sounding like a teacher, if we have X number of football players and X number of cheerleaders, well, who cares? The X's cancel out, and the ratio is still 1.85. This leads us to a very, very important concept. The ratio of the weights of a large but equal number of two different objects is the same as the ratio of the weights of one of each of these objects. If necessary, stop the video and think about this. It says that if I have 11^4 gazillion of one object and 11^4 gazillion of a different object, the ratio of the weights of all 11^4 gazillion of these objects is the same as the ratio of the weights of just one of each of these objects. Well, that's real nice, but what does this have to do with the mole? Well, let's imagine that you're in the laboratory and you have that problem that we were talking about. You want to run a reaction using barium and iodine, and you don't want anything to be wasted. So you go into the lab, and with great skill, you do the following. Now, we've already discussed the fact that the relative weight of an iodine molecule compared to a barium atom was 253.8 to 137.3, which was a ratio of 1.85. One iodine molecule was 1.85 times heavier than one barium atom. So here's what you do. You go into the lab. You reach into a bottle of barium, grab a sample, hold it in your hand, and sense its mass. Remember we talked about that in one of the earlier lectures? We'll pretend that you've gotten really good at this. Then you reach into a bottle of iodine, take out a sample, and you hold that in your hand. By the way, don't ever try this. Iodine will burn you, and barium is toxic. This is a hypothetical experiment. You hold the two samples, and you sense that the sample of iodine you're holding is heavier than the sample of barium. It's not quite twice as heavy. You've gotten really good at this. In fact, you've gotten so good that you realize that it's actually 1.85 times as heavy. Now, what does that tell us? Oh, sorry, I spilled these. What does that tell us? Well, we've already determined that one iodine molecule is about 1.85 times heavier than one barium atom. So if I'm holding a sample of iodine, which obviously has more than one molecule, and I'm holding a sample of barium, which obviously has more than one atom, but the weight of the iodine sample is 1.85 times heavier than the weight of the barium sample, I can say something very significant about these two samples. The number of iodine molecules and the number of barium atoms are equal. Back to our football player and cheerleader analogy. If you knew that a bunch of football players that you couldn't see were on a scale, and a bunch of cheerleaders that you couldn't see were on another scale, and the ratio of the readings on the scales was 1.85 to 1, you would know that you had equal numbers of football players and cheerleaders, even though you couldn't actually see them and count them. And the same is true for molecules. You notice that what we've been able to do is basically count out atoms and molecules, not by counting them directly, but by weighing them. Now you might say, wait a minute, you haven't said anything about the mole, and you haven't said anything about the actual number of atoms and molecules in the samples. We will later, but for the time being, that's not the important thing. Here's the important concept. Here is the bottom line. Here's what you should understand. I can, in essence, count out equal numbers of atoms and molecules by weighing them. It works like this. I know the relative weights of the individual particles. In other words, the ratio of the weights of one atom or one molecule of each. I can weigh out large samples of these substances so that the weights of the samples stand in the same ratio as the weights of the individual particles. When I do this, I know that the two samples that I weighed out contain the same number of atoms or molecules. That's what this mole thing truly allows us to do. Well, I suppose now we have to give a formal definition of the mole. What is its formal definition? You know something? I don't think that presenting you with the formal SI definition of the mole would actually be very instructive or useful. So I'm going to choose a definition of the mole that's not actually the formal definition in the SI system of units, but conceptually, it's what we need to understand. A mole of something is an amount of that substance whose weight in grams is numerically equal to what its molecular weight was in AMUs. Now you may react to this with a big what? I mean, what? What does that say? I mean, what is that supposed to mean? Well, let's look at an example to make this clear. We said that barium has an atomic weight of 137.3 AMUs. That's the weight of one barium atom. That's hardly any weight at all. If you want to talk about a mole of barium, you just take that number and change its units to grams. 137.3 grams of barium is something that you can see and something that you can handle. You can almost imagine what that might feel like. That is defined as 1 mole of barium. 137.3 AMUs represents 1 atom of barium, something I can't see or work with. But 137.3 grams of barium represents a mole of barium, something that I can easily measure out, something that I can see, and something that I can work with. I2, 253.8 AMUs for 1 molecule. Change those units to grams, and 253.8 grams of iodine would be 1 mole of iodine. So what can I say about these two samples? You might want to stop the video and think about that if you don't already know the answer. What I can say about these two samples is of great importance. What I can say is that these two samples contain the same number of molecules or atoms because both samples represented a mole of each of the two substances. And a mole of anything contains the same number of things as a mole of anything else. A mole of iodine weighing 253.8 grams contains the same number of molecules as there are atoms in a sample of barium weighing 137.3 grams. The reason the iodine weighed more was simply because its molecules were heavier. The same reason a certain number of football players would weigh more than the same number of cheerleaders. Now, how can I extend this concept? What about a mole of whatever? I might take something like water. Water weighs 18.0 grams per mole. Its molecular weight was 18.0 AMUs. We've done that calculation a few times already. And if I change the units to grams, then I'm talking about a mole of water as opposed to just 1 molecule. If I had a sample of water weighing 18.0 grams, that would be a mole of water. and it would contain the same number of particles as a mole of barium or a mole of iodine. So I come right back to the key idea of this lecture. A mole of anything contains the same number of things as a mole of anything else. And I say things because these might be atoms, as for barium, or molecules, as for iodine and water, or formula units, or for something like sodium chloride or barium iodide. Well, the obvious question to ask now would be, how many particles is that? We'll get to that a little later. But first, we must sharpen the skill. If you're going to be talking about a mole, and if we're going to count things not by weighing them directly, not by counting them directly, but by weighing them, then we must be sure that we know how to find the weights of moles of different substances. We actually did this in the last lecture, but let's try a few more since the skill is so important. Calculate the molar mass of nitric acid. Now, if you're a thinking student, this graphic should immediately raise a question in your mind. Namely, what is this molar mass thing? Well, I said that the weight of a mole is simply the molecular weight of the substance expressed in grams. We call that weight the molar mass, the weight of the entire mole of the substance. And I'd like to make another comment here. Technically, the term molecular weight refers to the weight of one molecule expressed in AMUs, while the term molar mass refers to the weight of an entire mole of the substance expressed in grams. For example, the molecular weight of water is 18 AMUs, while the molar mass of water is 18 grams. The first refers to one molecule, the second to a mole. But sometimes you may find the term molecular weight used when the more correct term would be molar mass. You may hear someone say that the molecular weight of water is 18 grams per mole, perhaps. Don't get hung up on those words. If the weight is expressed in grams, it's the molar mass, no matter what it's called. For nitric acid, the molar mass is fairly easy to calculate. The formula for nitric acid is HNO3. A molecule of nitric acid contains one atom of hydrogen, which weighs 1 AMU, one atom of nitrogen, which weighs 14 AMUs, and 3 atoms of oxygen at 16 AMUs each, for another 48 AMUs, which makes the molecular weight of nitric acid 63.0 AMUs. Changing these units to grams means that the molar mass of nitric acid is 63 grams per mole. So nitric acid has a molar mass of 63.0 grams per mole. A mole weighs 63.0 grams. If you had a sample of nitric acid in your hand that weighed 63 grams, you would have a mole of nitric acid. Again, not a good idea since nitric acid is very corrosive. These statements all say the same thing. If you wanted to give someone a mole of nitric acid for a birthday present, you'd have to go to the nitric acid store and buy 63 grams of the stuff. Let's do another. Calculate the molar mass of sucrose, C12H22O11. Okay. 12 carbons at 12 AMUs each is 144 AMUs, plus 22 hydrogens at 1 each is another 22 AMUs, plus 11 oxygens at 16 each for an additional 176 AMUs, gives us a total molecular weight of 342.0 AMUs per molecule, or a molar mass of 342.0 grams per mole. And a final one. Calculate the molar mass of barium phosphate, Ba3PO4 taken twice. As I work through this problem, listen carefully to my exact words. They will touch again on the difference between talking about one molecule, atom, or formula unit and a mole of something. One formula unit of barium phosphate contains 3 atoms of barium at 137.3 AMUs each, which is 411.9 AMUs, 2 atoms of phosphorus at 31.0 AMUs apiece for another 62.0 AMUs, and 8 atoms of oxygen at 16.0 AMUs, which is 128.0 AMUs, for a total formula weight of 601.9 AMUs. Changing the units to grams says that the molar mass of barium phosphate is 601.9 grams per mole, which, by the way, is sometimes called a gram formula weight, although I'm just going to call it a mole. And now comes what might be called another critical moment. Let's suppose you had a birthday party and you got 4 presents. One of your cousins gives you 18.0 grams of water. You open up another present to find that this friend gave you 63.0 grams of nitric acid. You open up a third present that contains 342 grams of sucrose, C12H22O11, and you open up a final present and it contains 601.9 grams of barium phosphate, Ba3PO4 taken twice. Now I'm going to ask you a question. I want you to pause the video if necessary and think carefully about the answer. Which of these presents would contain the greatest number of molecules, and which of these would contain the fewest number of molecules? Ignore the fact that barium phosphate is an ionic solid. Pretend everything here was made of molecules. I asked that question in kind of a tricky manner. I asked you which of the 4 samples contained the greatest number of molecules and which contained the smallest number. There is a great temptation to just blurt out that the sample of barium phosphate must contain the greatest number of molecules since it has the greatest weight. And water must contain the fewest number of molecules since that is your smallest weight. But if you have really understood this lecture, you will realize that the correct answer is none of them. They all contain the same number of molecules, because each of your friends gave you a mole of something for a birthday present. All moles have something in common. They all contain the same number of particles. Now you might wonder, gee, you mean these things all contain the same number of particles? Absolutely. And that's a critical idea. 18 grams of water, 63 grams of nitric acid, 342 grams of sucrose, and 601.9 grams of barium phosphate all contain the same number of atoms, molecules, or formula units, even though they have different weights. Because these amounts all represent 1 mole of each of these things, and a mole of anything contains the same number of things as a mole of anything else. Now let's go back to our barium and iodine reaction. If you wanted to run this reaction with nothing wasted, you could in fact weigh out 137.3 grams of barium and 253.8 grams of iodine. Since 137.3 grams is 1 mole of barium and 253.8 grams is 1 mole of iodine, you have weighed out equal numbers of particles. In essence, you have counted out equal numbers of barium atoms and iodine molecules by weighing them. Now you might say, well, yeah, but what if I don't want to use that much of each substance? Those are pretty big weights. Fine. Then use half as much of each, or a third as much, or a tenth as much. It doesn't matter, just so long as you weigh them out in a weight ratio of 1.85 to 1. The mole concept has allowed you to count atoms and molecules. Of course, now I assume that you are curious as to how many molecules are actually contained in 1 mole of something, since all moles contain the same number of particles. That number is enormous. It's equal to 6.02214 times 10 to the 23rd, which we usually round off to about 6.02 times 10 to the 23rd. Many teachers and students prefer just 6 times 10 to the 23rd, and that's fine. And it has its own name. It's called Avogadro's number, in honor of an Italian scientist named Amedeo Avogadro. Although, interestingly enough, Avogadro never had any idea as to what this number might actually be. He lived too long ago for that. Avogadro's number wasn't determined until many years after his death. We're actually going to be talking about Avogadro and his work in Lecture 12. It's an interesting story as to how that number is determined. Obviously, no one sits down and counts out atoms by hand. There are actually a few different ways that this number has been determined. Discussing these ways is beyond the scope of these lectures, but it might be covered in a more advanced college or perhaps an advanced placement course. This is obviously an enormous number, far too large to really comprehend on an intuitive level. If every person on Earth were to start counting the number of molecules in just 1 mole of something and were to count at a rate of 1 molecule every second, never stopping for anything, not even to study chemistry or work mole problems, it would still take them over 3 million years to finish counting. And the units on this number are important. We will use the units of molecules per mole. So let's summarize the key idea we've been discussing. All moles contain the same number of particles but have different weights because some molecules are heavier than others. And the number of particles in a mole of anything is equal to 6.02 times 10 to the 23rd particles. In fact, 6.02 times 10 to the 23rd of anything can be considered to be a mole of whatever it is. Think about it. If you were wealthy enough to have 6.02 times 10 to the 23rd dollars, what would that make you? Why, you'd be the world's first millionaire. Some teachers like to draw an analogy between the concept of a mole and the concept of a dozen. If I asked you, what is a dozen? You would certainly say 12. If I asked you, what does a dozen weigh? I think you would immediately realize that this is a pointless question and would ask, well, a dozen of what? If I walk up to you and say, what is a mole? You should smile from ear to ear and say, a mole is 6.02 times 10 to the 23rd. But if I ask you, well, what does a mole weigh? You should look at me and say, that's a silly question. It depends upon what it is. It depends on how heavy the molecules are. If you're talking about a mole of water, water molecules aren't very heavy. It would only weigh 18 grams. If you're talking about a mole of nitric acid, those molecules are heavier. It would weigh 63 grams. If you're talking about a mole of sucrose, you'd need 342.0 grams. And if you're talking about a mole of barium phosphate, wow, that's really heavy. It would take 601.9 grams. All moles contain the same number of particles, namely 6.02 times 10 to the 23rd, but what they weigh depends upon what they are. In the next lecture, we're going to work several mole problems. As we work these problems, we're going to apply those simple quantitative reasoning ideas that we talked about in a couple of the earlier lectures. You may even want to go back and look at them again. If you really understand the mole concept, you shouldn't have too much difficulty in working the problems. I'd like to end this lecture by putting in a plug for National Mole Day. Believe it or not, there is such a day. It is celebrated each year on October 23rd, from a couple of minutes after 6 in the morning until a couple of minutes after 6 in the evening. I'll leave it to you to figure out why that particular day and those particular times were selected. If you are interested in learning more about National Mole Day, just plug this phrase into a Google search. Can't wait until the next lecture when we actually get to solve mole problems. See you then.